Welcome back, all of you, to the concluding session of our data science tutorial using the PUBG dataset. If any of you have not seen the first session of this tutorial, you can check out its link in the description box below. So now let's get straight into our model, where we shall finish our analysis. Now, the next part is about cleaning out your data to better your data so that you can lay your analytics on top of it. Here we are going to deal with something known as outliers. We are going to try and detect them in our model as well as remove them, which basically means we're going to try and find out the fraudsters or imposters in the game. Now, an outlier basically means a value that lies outside of your general pattern or curve of your data, as I had shown you in the box and whiskers plot earlier. Once you remove them, it actually helps homogenize and improve your model. But the question is pertinent: how do we do this? How do we catch the imposters or fraudsters in the game? So for this particular section, we are going to be looking at some very absurd statistic that we find in our game. These outliers have to have a reason so as to why they are so good, why they are performing so well. I understand being at a certain skill level, so you have a certain amount of accuracy. But then there are certain numbers, certain statistics which are just not possible. So I'm going to run through this section fairly quickly. Basically, anything that seems like an anomaly, we are going to try to detect and in the process omit. Hence, we are going to try to homogenize our data sets. Yes. So first of all, I am dropping the illegal matches, which basically means the not applicable match. And then we're going to determine the shape of the data, which will give you the dimensions of your data set. Now we need to understand that in every game that is popular, people come up with cheats, people come up with bots, and that is part and parcel of wherever you game. You may game on Steam, you may go ahead and game on any other platform, and in any other game, may it be PUBG, Dota, Counter-Strike, a bunch of other games. The use of automated aiming software is without a doubt one of the most powerful cheats that you can use. And it is definitely used in PUBG at this time. Basically, what it allows you to do is it's going to bind a key to your mouse, or maybe sometimes auto aim, or have an aim and lock on function, which is automatically going to make the targeting of an enemy in line of sight much easier. If you're playing in, suppose, a squad or a duo, your other group members may not be able to use it, and you can have a bot for you, a sort of a trigger bot for you, which can be set automatically for your targets. Yes. Now, how are we going to try to find it? Yes, there is obviously a normal number of everything that is possible during a certain game. What we are going to do is pick out the weird statistics, the weird ones from the entire data set, and we're going to attempt to drop them. So first of all, total distance traveled by a player, which obviously sums up your riding, walking, and swim distance. So this is where again feature engineering comes into picture. We are creating a new feature called total distance. Now, what we're going to do is we are again going to create another new feature which is called headshot rate. Now, for most people, if you shoot 10 people, max to max, 1 or 2 of them are going to be perfect headshots. However, there are certain anomalies when you look at the data set that we have. Now here we are also going ahead and defining certain functions for plotting graphs, and we'll be needing a lot of it later in this section. We'll be using a lot of count plot and distribution plots for this. So we're just defining them beforehand. Here come the anomalies. Firstly, inhumane kills. Now, as I mentioned, there are certain weird statistics in our dataset. These players apparently have such high accuracies. Now, there are some people with an inhumane number of kills. Now, these people might be just having fun, or could be fraudsters, or just living their ultimate shooter range dream through this game. So removing these outliers might simply just improve our training set just a little bit. Here, can you see? Now this is what the kill plot looks like. The kill counter plot generally looks like. But we picked out certain outliers and plotted them all. Here are their IDs, the group IDs, the match IDs, and their stats. Now, one thing that I see pretty common here is, do you see how little the walk distance is for the number of weapons acquired by each of these players? They have gone like 20 to 23 meters, here 85 and 46 meters, acquired more than 60 weapons. Look at their longest kills and the amount of headshots that each of them have put up. Now you have to stop and think about it yourself. Is it even possible to kill that many people by acquiring more than 60 weapons and maintaining a total distance of less than 100 meters? Obviously not. Hence, either these people are extremely talented or just plain imposters. Then again, if you look at the next table, you look at people who've had 40 headshot kills. Oh my God, there are 42 kills. Out of 42 kills, there are 40 headshots. This second person out of 43 has 34 headshots. And they have used 0 boosts in total, despite having been knocked down 40 and 30 times. Is such a thing even possible? Their headshot rate is nearly perfect. All of their headshot rates are nearly perfect. Even if their weapons acquired are fairly normal, I'm just looking for the heals here. All of them required no heals and no boosts at all, despite having been knocked down 40 times. Obviously, again, that is not possible. Then we have a couple other fraudsters. So what we're going to do is we are going to drop these fraudsters and clean out our data set a little bit. Next, we have more people with 100% headshot kills. Now, this is the headshot rate of people. There are people with 100% headshot kills, but that is only up to, say, people with 5 headshots. But do you see the outlier? The outlier goes up to, I think, 15. Now here is a list of all the hitmen who made more than 10 kills, and all of them were perfect headshots. Now there can be 2 reasons behind these. Either these people are literally virtual sniper gods and goddesses, or they are cheating, plain and simple. But I've decided to keep these players and not delete them for now, because we wouldn't know for sure, because the numbers aren't that great. They go up to like barely 13, 12, 13, which I can still understand somebody with high accuracy might do. And they have a fair amount of boosts and heals, which makes the data slightly more believable. So we're going to keep them for now. Next, we have killing without moving. Again, it's the same thing all over again. There are imposters who are just going kill after kill after kill, even without moving. So first, what we're going to do is we're going to identify the total distance traveled by a player, and then we're going to set a Boolean value to true if they go ahead and make kills even without moving a little bit. And we have a couple of people who are extremely talented that they're just going to stay at one place and just kill everybody around them without having to move at all. Now we're going to drop this because quite an anomaly. Then we have the longest kills. And here we have our longest kill bar plot, where we see as the distance goes on increasing, the chances of kills get decreased. Here you can see the longest kill is all over 1 kilometer. Now, is it even possible that somebody is shooting from that far away? In my opinion, it's not possible, and thankfully, it resonates with the opinion of the creators of the game. Hence, we're going to drop these as well. Now, we're going to drop people who have more than 10 roadkills. Oh, I just have to show you one really funny thing. Notice how the first ID over here, look at the number of roadkills this person has. It has 14 roadkills, and literally the ride distance is 5 meters. How is it possible? Did you stack up, did you pile up all the different men on top of each other and run them with your vehicle? That's obviously not possible, and hence we are going to drop this fraudster. Now, another anomaly that is very consistently found is an anomaly in traveling. Now, this entire PUBG map or area or island is a 64 square kilometer map. And if you look at it properly, you'll see that each of these yellow boxes represent 1 kilometer square. So first, we have taken out the walk distance, ride distance, and swim distance, the overall swim distance, the mean, standard, minimum, maximum, so on and so forth. We're again going to have a distribution plot of all the walking that happens. How far does somebody go? Obviously, nobody is going to walk for 25 kilometers, but still there are people here, which surprises me. Now, I didn't come into this hoping that I would find somebody that has walked 25 kilometers throughout the course of the game, but it might be, I think, digital wanderlust, I guess. But who am I to judge? Now, there are these wanderers and travelers who just play to roam around and explore places without killing anyone. But then again, don't you think, how are they traveling 13 kilometers and 25 kilometers in a game? So what do we do to them? We ditch them, of course. Now we're going to do the same things for riding and swimming as well. Take a better look at it when you go through this model on your own. But I'm basically doing the same thing for riding and swimming that I did for walking. Now, this is also funny. How are these people swimming for 2 kilometers without even breathing? Video games are so extremely realistic these days. If something doesn't happen in real life, you can be mostly sure that it cannot happen in your video game. Apart from traveling, we also see other anomalies, such as anomalies in the weapons acquired, as I had mentioned before. People who have acquired more than, say, 80 weapons throughout the course of the game. The maximum somebody's acquired is 128 weapons in one game. I don't understand, what would a person do with 128 weapons throughout the course of this game? Is opening a shop an option in this game? I don't know. If there is, you guys tell me. Then we have anomalies in heals. Now, for most of you regular players, you would know that most players use like 5 or 6 healing items or less. But then what if somebody goes ahead and uses 30 or 40 healing items? Again, are you going to stack them up at this time of coronavirus? Because, my friend, you cannot bring digital medication to real life. Somebody should have told them. So we again remove these outliers. Now, this is a very important question that you should ask yourself. As you saw, I removed most of the outliers except one or two. This is a very important question that you as a data analyst should be asking yourself. Should you be removing all the outliers that you ever find in your dataset or not? Now, for that, you need to understand that in analytics or data science, there is no fixed strategy through which you can approach a model. There's no right way. There's just a more and more efficient way to do this very same thing. 5 data scientists will have 5 very different approaches towards this very problem and this very PUBG data set that I'm using. In my opinion, in particular, imagine an entire sea of water. If you just picked out, say, 10 buckets of muddy water from the shore, it would not particularly cause a deficit in the sea. but it keeps your shore clean and makes it look good from your closest viewing point. So it's kind of like the same when it comes to data. In our case, we have millions of rows. We have sometimes thousands and millions of rows. So if you lose like a couple thousand of them and it helps you create a better model, go ahead, do that. But make sure you assess the outliers properly before you choose to ditch it from your model. Like you might have noticed, I took out every single outlier that I found except one, the one with the perfect headshots. That is because even if it was an anomaly, I couldn't for sure say that everybody in that list cheated. If I would have dropped that particular anomaly, it could have costed the efficiency, the accuracy of my data set, as some of them might have been genuine. I know people who have 5,000, 6,000 hours of gaming, and they are actually pretty good. And they do have perfect headshot scores in certain games that they play. But then again, I know a lot of them are fraudsters and imposters. But if, again, I cannot afford to lose the good statistics for making sure I'm ditching the bad ones or the ones with a bias. So what I'm going to do here, I'm just going to create a checkpoint because this is a fairly long model. So at this moment, our data is clean. So I'm going to save it to a separate CSV file and put it in the same drive that had my other files. And then I'm going to import pandas as PD and again do the whole cleaning data, reduce the memory usage of this particular data set and reduce it for the sake of efficiency of the model. Now this might take some time because you are exporting data into a CSV file and you're basically putting it into your drive. That's going to take some time. And then once you're done with that, you're going to import your pandas, your library. And then reduce the size or the memory usage of the dataset you've just saved in your folder. Moving ahead, we have a ton more features to add. So let's go ahead and start experimenting with our data a little bit. So we are going to be adding and removing some new features and finding their direct correlations with the winning probability. Now, there are a couple things this dataset is missing. Now, all of us know that in a single round, there's a cap, there's a limit of 100 players in every game. But most of the times, as we have seen previously while looking at our data, we know that the game is in full. A complete 100 players are not playing the game. And there is no such variable in our current data set that gives us the exact number of players that have joined. So let's go ahead and create one. So this is what the data that we've saved looks like, the cleaned data that we just exported. Yes, this is the head of the data. And here we have a variable and a graphical representation of the number of players joined. We have the number of players joined and the count of how many times there has been that particular number of entrants in a certain game. So as we can see, the most number of times there have been 91 players. And if you remember, we had actually determined this in one of the cells above where we had 91 point something or 90 point something players as our maximum number of players. Now there are very few matches, a couple matches only with less than 75 players. As you can see, below 75, there are not very many matches or counts. Most of the matches are nearly completely packed. And why not? this game blew up so hard and it expanded its horizon from all your desktops and PCs to mobile gaming. So you could be sitting anywhere and making 20 perfect headshots and swimming for 2 kilometers without breathing. It's completely your choice. Who am I to say? So yeah, this game made a lot of noise when it came out, caused a lot of controversies, which actually caused a lot more people to be aware of this game and join this fraternity. So I'm not actually shocked that there are very few games which are not completely jam-packed with players. So now that we have a feature which has the number of players join, we can normalize all the other features based on how many players are there per game. Now, these can be a number of features from the kills, the damage dealt, the maximum place, and the match duration. So again, we're going to start out by creating normalized features and then going ahead and comparing the standard features and the normalized features. And then you can get a great side-by-side comparison of each feature on the left and its normalized variable on the right. So you have kills and your normalized number of kills per player. Then you have damage dealt and the normalized damage dealt on the right, so on and so forth. You have for max place and match duration. After that, we are going to take all this clean data and try to establish a correlation between all of these attributes. Again, more correlation is shown in green and less in brown. As you can see, now with the clean data, we have a much smaller correlation matrix. We can see walking a certain distance still contributes a lot, in fact, contributes more to the probability of winning a game. And the damage dealt percentage also contributes greatly to your placement in the end. Then we have a couple more variables. We have health items, we have headshot kill rate, we have kill place over max place, over walk distance, over total distance, and per distance per second. We're going to also create a heat map off of that. Then we are basically again mapping them on a heat map. Now you have a better idea with these new attributes as to how your probability, your chances of placing in a game are affected by different attributes. I understand the distance that you walked has a good correlation with your winning percentage, but what matters slightly more is the distance that you walk per unit time. Then a great contributor towards you winning is also your health items. Just things like that which make analyzing data all the more fun. Next, we basically ask the cell to return to us the shape of our data again, the dimensions, and we're going to drop a couple more attributes. Now our clean data head looks something like this. And then we have this heat map correlating all the attributes that we have created so far or that has been provided to us by the dataset. Now, all the positive attributes are fine and so are the negative ones. What we do not want are the zeros and the ones that are close to zeros, which basically means that those attributes do not affect your probability of winning at all. So why do we even need them? Because our ultimate goal is to find out the value of the variable. We are trying to find out each and every player's chances of winning in a said game. So what we're going to do is we are going to remove all those features which have absolutely no impact on your winning probability. So now, as you can see, our clean data From where we started with 4.4 million rows and 28 columns. Now we have 4.1 million rows because we just went on cleaning and cleaning and cleaning our data more, and we have 35 columns, which means we have more attributes, but we have cleaned the data within those attributes. Now with that comes up your next assignment. Now we have already removed all the zeros from your heat map. But do you know what else is useless data? All of these ones. Now the correlation of any attribute with itself is definitely going to be 1. Here you can see the players in team Y in this axis and in this axis. Basically the same thing, and hence perfect impact. Because players in team Y is 100% going to affect players in team Y. It's the very same variable. The existence of it affects the existence of it, right? So go ahead, you can download this model and do it as a part of your assignment. Again, do not forget to leave your approach in our comment section. I would appreciate greatly if you did that. We also love to look at our learners community growing and learning with us. So I'd highly encourage you attempt these assignments at least. Give them a try. Now we are basically modifying our test data. And we have nothing but highly correlated data, which we are again going to save into a CSV file, and we're going to put it in the very same folder that we had created earlier. Now, as that happens, let's move on to our final prediction, because as I had mentioned earlier, putting it in a CSV file is going to take some time. It's 2 million rows after all. With that, we've moved on to our final prediction. Let's go ahead and look at our problem statement one more time and determine our target variable. Basically, we are trying to create a model that forecasts or predicts random players' finishing placement in any random given match at any random given point in time based on their final statistics of all the matches they've played so far on a scale of first place to last place. Your target variable here is the win place percentile. This is the percentile of winning placement, where 1 corresponds to the first place and 0 to the last place in the match. So our objective right from the beginning is to determine this percentile. Now, depending on what kind of goal or objective that you are looking for from a certain model, tells you a lot about the machine learning technique that you would want to preferably use to get to your objective. Apart from that, the target definition tells us a lot about how it's distributed. So what is the metric? Now, how do you decide what is a metric, what is a unit of decision for you to choose between all these different algorithms that are available to you? Ideally, a professional would use a ranking algorithm, something like a lambda rank. Now, learning to rank, or LTR, refers to a class of techniques in supervised machine learning which help you solve problems like these. Essentially, you treat it like a regression problem. And what your algorithm does, what your procedure does, is that it compares different pairs of items and then arranges them or sorts them in ascending or descending order as it iterates through various different random pairs to extrapolate the final ranking of all the items in that particular column. Now, the business metric is the rank and not the mean absolute error. But as such, we are going to optimize our algorithm, make it efficient using the mean absolute error objective. Now, there are a couple of limitations for sure, such as the outliers and to some extent the ununiqueness of predictions, but we're going to deal with it, and this is also the most straightforward way to do it. Now, as it might have been already pretty much been established throughout this model, that our target variable is the percentile of winning placement. Now, in this particular game in PUBG, all of the teams get assigned a percentile value, so there would be approximately the same count of your zeros, 0.5s, 1s, etc. Now, there will be some irregularities in the distribution, again, due to the imbalance in the team sizes or the number of teams. Now, what you should be expecting is to see uniform distribution and a Gaussian distribution with a mean of 0.5 to go with it for an average percentile score per match. So we're going to start out again by taking our CSV file of the highly correlated data and reduce the memory usage of that particular data set. Now that the memory usage has been decreased by almost 60% and we know the shape of our data, we are also going to be dropping match ID and group ID from our training and testing data sets, because they are of no use to us. And finally, we have the dimensions of our training and testing data set. Which leads me to our next section, which is to deal with categorical variables. For this, we are going to hot encode the match type feature and use it in a random forest model. So what is a random forest? It's basically a machine learning algorithm, a supervised machine learning algorithm, which is used for regression models like us. It's also used for classification models, but that is a case for another day. Now, they're extremely simple to build and interpret, but then again, it has its own pitfalls as it is less accurate, one-dimensional, and inflexible when it comes to classification. But it wouldn't throw us off so much as we have a regression model in mind and not a classification model. To explain to you a random forest in very simple terms, imagine a person that you know, Chandler, or maybe you are planning to go on a vacation. It's a 1-year-long vacation, so you decide what places you want to travel to, and you take suggestions from a bunch of your friends. Now, obviously, your friends want to know your preference and ask you different questions before they recommend you places. Now, after talking to all of them, you decide to get a vote and hence go to the place which has most votes. Now, this is a typical example of a random forest algorithm. Basically, what it does is that this algorithm uses ensemble learning method in which various different individual results combined form the result of a random forest. Now, there are a couple of different types of ensemble learning, such as bagging and boosting. Now, this is what your typical algorithm in very simple terms is going to look like if you take the example of you taking your friend's advice to go on your year-long trip. What you're going to do is you're going to select some random subsets of data from, say, an entire data set. You're going to talk to all your friends separately, basically train your decision trees. And when each of the individual people predict, or in your case, put in your vote, you then collect the results of all the voting of all your different decision trees or your friends, and then make your final choice or make your final prediction. The final prediction is always the one with maximum votes. Now let's go ahead and see how we can use it in our model. Now, first of all, we are going to determine the number of match types, which we know are 3 kinds of match types: solo, duos, and squad. Now, one hot code for those of you who do not know, in digital circuits and machine learning, it's one hot is a group of bits among which you can make legal combinations of values with a single high bit, or like 1, and all other low bits, which are zeros. The 0 ones are also called one cold. In statistics, mostly dummy variables represent a very similar technique for representing categorical data. This basically is a process by which categorical variables are converted into a form that could be provided to your machine learning algorithm so that your model does a better job. Here you have one hot encoded all your match types. Now, there are a lot of group IDs and match IDs, so one hot coding them is basically computational suicide. So what we're going to do is we're going to turn them into category codes. That way, we're still going to benefit from the correlations between groups and matches in our random forest algorithms. So first, we're going to start out by turning our group ID and match ID into categorical types. Then the next two lines are basically to get your category coding for your group ID and match ID. And finally, we are going to get rid of all the old columns. Then we're going to go ahead and drop the ID column because probably it won't be the most useful for our algorithm. Your test set contains different IDs, so I think it would be wiser to drop them out. So we're going to do that. Now, we are going to get prepared for our machine learning model. Let's start by sampling. We'll take a sample of 500,000 rows from our training set because obviously we can't take 4 million rows together. It'll be extremely hard for debugging an EDA. Then, as you saw previously, you're going to split your decision trees using your random subset of features. Our entire data set in tabular form, once it has been reduced, is basically a data frame. And we're going to split the training data and target variable, where y is going to be our target variable and your data frame or df is going to have all the columns except your target variable. Then we're going to split the training and validation data, and we're going to print the dimensions of our sample training, target, and validation data. And finally, we're going to print our dimensions of samples, which are our sample training shape, target shape, and validation shape. Now we have our data, but we have to see how accurate it is. So we are going to define the function for calculating the mean absolute error, as I had previously mentioned, for seeing the reliability of the model that you've created. So we are going to use the scikit-learn library for metrics and ensemble, and we're going to import the mean absolute error function as well as the random forest regressor. We're also going to define a function to print the mean absolute error score of our model, and then we're going to train the basic model. Here you have your estimators, your minimum samples, your max features, and your jobs. Then we're going to find out what are the most predictive features according to our basic random forest model. In order, you have your walk distance percentile, walk distance per second, kill place, percentage, walk distance, all the way down till a ride distance. Then we are going to plot an importance graph of the 20 most important features, and you can see in a graph form what you previously saw in a tabular format. And you can see the walking actually affects a lot of your winning percentile. Just some more training and indexing. We're going to keep all the significant features. And finally, we are going to build a data frame with only the significant features. So now we are going to be taking those features and building a random forest model with those features. So we are going to train the model with our top features. Then what we're going to do is, let me go ahead, run this. We have to train our model on the top features and get their feature importances respectively. And here we are, again, a very similar plot. And then we're going to execute a dendogram to view very highly correlated features that contribute to our winning percentile, our winning placement percentile. For that, we are going to be using a library called SciPy. So here we basically have a dendogram. Now, for those of you who do not know, this is a plot which is used for hierarchical clustering. Yes, so you can basically see the hierarchy of correlation of the different attributes. You can also see little clusters of what directly or indirectly depends on what attribute. For example, here you can see that the boosts and health items are basically one cluster, but they are again dependent upon this whole walking and distance covered and basically how tired certain. Then we're basically going to define a function to get a random sample of rows from our data frame. Followed by installing a couple of packages, a couple of libraries. And we're basically just able to see the head of our data frame, which is the first 5 lines. We can see your IDs, we can see all the attributes. Then we're going to use the PD box that we have just installed, and using that we're going to plot the predictive quality of kills. And the entire thing is using ggplot. We see how the walk percentile per kill percentile affects your placement. We're going to do the same for the quality of walk distance. And here we see it's a fairly more stable logarithmic graph. Then we're going to prepare our data and train our final model. Basically, you should try to increase your N estimators and playing around with different parameters to get better results. We're going to get our test datasets ahead as well as our training datasets ahead. Now, this might also take some time, so kindly be patient. Then again, we reached our final checkpoint where we are going to put up our modified test data as a CSV file again in the same folder on the drive. Now, in the end, let's add the same features, the same attributes to our test data that we have in our final version of the data. We have our walk distance percentile, we have our kill place over max place, players joined, the kills norm, damage dealt norm, all of those extra attributes that we generated through feature engineering. Then we're basically going to be turning our group ID and match ID into categorical types and get the category coding for both of those. And finally, remove the irrelevant features from our test dataset. Fill the non-applicable fields with 0, which basically means that they're going to be temporary. And with that, finally, we're going to be predicting the final percentile of winning placements. Now we are going to put in our data frame, create a submission file, and import it to our CSV. Now I've already done this one time before. And let me navigate to our submission file. This is what our submission file is going to look like after all of this hard work and code running. This is what your data should look like. You have 2 columns basically. You have your player ID and their placement percentile. Obviously, this will not give you a unique percentile, but you need to understand that we're talking about 4 million rows of data here. obviously the top 1 percentile is going to be a lot of numbers. If we have 4.4 million people playing a certain game, the top 1 percentile is going to be like 40,000 people. With that, I come to the end of my model as well as the end of this session. Don't forget to check out other content in our data science playlist as well as our data science certification training, the link to which will be in the description box below. For now, I'd like to conclude saying that data science actually continues to evolve as one of the most promising and in-demand career paths for professionals. To be a successful professional in this field, you must understand that you must advance past the traditional skills of analyzing large amounts of data, data mining, and typical programming skills. You must master a full spectrum of a data science lifecycle and possess a level of flexibility and understanding to maximize returns at each phase of the process. Data is everywhere and it's ever expanding, and a variety of terms related to it are often used interchangeably, but don't let that get into your head. It's actually not that complex if you put your mind to it. So why not turn this quarantine into a learning experience by upping your skill and finding something new to learn? I shall leave you with that thought. My name is Upasna. Thank you and have a great day.